quickly recap what we have discussed. So this is one of the alternative methods used to derive element equations and stiffness matrix, and this method is a more advantage compared to other methods because it involves not only the element equation along with stress strain. So this method is more adaptable for determining the element equations for complicated elements. So not only one thing, you can use this equation for 2D and 3D as well. This method is only applicable for elastic materials. So these are some of the important things of potential energy. So the total potential energy is defined as the sum of internal strain energy and the potential energy due to external forces. Okay. That is one thing we have to understand. The strain energy is what is the strain energy? Strain energy is the capacity of internal forces to do work through deformations in the structure. And external forces, body forces, surface traction forces, nodal forces that do work through deformation of the structure. So there are one is the strain energy that is coming due to internal forces, external forces energy from external forces. These two forces will give total potential energy. So we can derive stiffness matrix and other elemental and model equations using this minimum potential energy theory. That means the total potential energy of the system should be minimized to derive stiffness matrix and other things. So to minimize this, we need to differentiate the total potential energy. So the total potential energy will be in terms of displacements. You see this equation. So if you see this equation, this total potential energy will be in terms of displacements. So when you try to differentiate with these displacements, we can achieve stiffness and other elemental and nodal equation. So this we have discussed last week. So this is the strain energy given for spring. Okay, half kx square. And my audio, video, and screen sharing. Just post your response on the chat. So this is the strain energy for the spring, and this is the Fx is the external force related energy. So when there is external force is acting on the body, then the summation of node displacement at the node and forces. Okay. If you have 10 nodes, it will be 10. If it is 100, it will be 100. So the total potential energy equation is given by this equation. If you put together everything, this will come as the total potential energy equation. So this sign indicates that the potential energy lost when there is an external force is applied on the body. So these are the three external forces generally act on the body. One is body loads, one is surface loads, one is nodal loads. One is acting on volume, one is acting on area, one is acting on point. Now coming to, this is the equation related to 3D, so I will stop here. Let us not discuss too much complicated things, so we will stop here and we will proceed to another theorem. And then the Castiglione's first theorem. For any elastic system, in equilibrium, the path is constant. Okay, it is having some strain energy. When you differentiate strain energy with respect to deflection at one particular point, like suppose if you try to differentiate strain energy with respect to deflection at this point, it will give the differentiation will give the force value, nodal force value at that point. So same thing is represented here. du by delta 1 gives F1, du by delta 2 gives F2. So let us write what is the total strain energy. Total strain energy is given by half into kx square. So where x is delta 2 minus delta 1. Okay. That is the deflection given in this way. So this is the deflection in the spring, half k delta 2 minus delta 1 whole square. When you try to differentiate delta u by delta 1, nothing but k into delta 1 minus delta 2 equals to F1. Similarly, k into delta 2 minus delta 1 equals to F1. These are the two equations we got it using differentiating strain energy with respect to deflections. Okay. So when you try to put it in matrix form, again we got k minus k minus k into delta 1 delta 2 equals to F1 and F1 and F1. So this is one theory, Castiglione's theory. Now coming to principle of virtual work. What exactly is the principle of virtual work? A body is in equilibrium if internal work equals to external virtual work for every kinematically admissible displacement field. Kinematically admissible means all the necessary boundary conditions need to be satisfied. Okay, it should not have any rigid body motions, anything. It should be so when you try to apply any constraints, it should be equilibrium. It should not have any rigidity. So this is giving internal strain energy, and this is giving energy due to external body loads. Okay, this is energy due to external surface loads, and this is due to energy due to external point loads. So internal strain energy is equals to all these loads due to external forces. Summation of all these loads due to external forces. And some other things. One is a Rayleigh-Ridge method. Rayleigh-Ridge methods it involves it will assume a displacement field u, v, and w. Okay, where u is given by a factor a1 to function of xyz. Similarly, v is nothing but aj into function of xyz, and w is nothing but function of xyz. So all these three functions are polynomials. So here the displacements u, v, w must be kinematically admissible. That means it should satisfy the boundary conditions. And there are boundary conditions in the body. Those boundary conditions should be satisfied by these polynomials. So the total potential energy equation is given by this one. So when you try to minimize this potential energy with respect to A1, so this potential energy will be given in terms of A1, A2, A3, A. So when you try to, we need to minimize the potential energy with respect to A1, A2, A3. Then we can get the equations related to stiffness matrix, element and nodal matrix. So these two are principle of virtual work, Rayleigh-Ridge methods are a bit advanced methods. You can refer on this information. Coming to let us discuss on functions. So let us understand about shape functions. That too only here. Then we'll try to understand more part later. So displacements measured in each elements are assumed to be a function of nodes. So if you see a typical bar element, ING are nodes, and this is the element. So we need to have some relation between element and node. Okay, the element and node are related using some function. Okay, so that function is nothing but shape functions. Okay, the displacements in elements are related to interpolation function known as shape function. Okay, assuming displacement u in the element varying linearly. So let us assume a function, displacement function linearly varying, that is a1 plus a2 to x. So let us put some boundary conditions. Okay, at x equals to I, we have displacement of ui. At x equals to z, we have displacement of uz. So when you try to put these boundary conditions here, let us see how. How it looks like. Now the function looks like this. Okay. Now we try to rearrange this equation in terms of ui and uj. Okay. Then displacement function is nothing but xj minus x. Okay, by xj minus xi ui plus x minus xi by xj minus xi to uj. Okay. So we can write it as u equals to ni ui plus nj uj. So ni is nothing but this factor and this factor. Okay, nj is nothing but this factor. So if you see here, here ui is known, uj is known. So the shape, the ni and nj are shape functions. So this is a one shape function and this is one shape function. They are dependent upon x value. Both the shape functions are dependent on x values. Now these are the shape functions. Ni is nothing but xj minus x by l. L is nothing but the length of this one, that is nothing but xj minus xi. Similarly, nj is nothing but x minus xi. So this function can be written in these terms. Okay, u equals to n matrix u matrix. Okay. So now important thing comes about what exactly shape functions. Okay, shape functions describe how element behaves. Okay, so basically it will tell this shape functions associated with the element will describe how the element behaves. Okay, so how it will be deflected. Okay, how it will capture the physics of the problem. Everything it will depends upon the shape function. So one of the important aspect of shape functions, if you take there are several elements in the stress analysis, the shape functions will differ from one element to other element. They are no way connected between one element to other element. So shape functions depends upon lot of number of nodes and type of physics it will undertake, and several factors will be there. So if we take particular element, it is suitable for one type of problem, and it will have number of nodes peaks. So definitely it will have one unique shape function associated to it. So another thing is sum of shape functions always unity. Okay. So when you try to suppose, for example, if you try to add these things, okay. So minus 1 minus plus x will get cancelled. Xj minus xi will be nothing but L by L will give 1. So sum of shape functions always unity. Shape functions has a value at 1. Has a value of 1 at its corresponding node and 0 at other nodes. So, for example, ni will have 1 at here, 0 at here. For nj, we have 0 at here, 1 here. Okay. So, shape functions have value of 1 at its corresponding node and 0 at other nodes. Now, let us understand displacement function. Okay. Displacement function is nothing but n into u. N is a shape function, u is this displacement function. So strain is by, for 1D problem we already discussed, strain is given by 2u by differentiation of the displacement function by x. So when you try to differentiate with these things, u will be taken it out and dn by dx. Okay. So here n we have n is shape functions. So when you put n values here, that is coming as xj minus x by L, x minus xi by L. So when you try to differentiate, the x factor will go and it is minus 1 by L and 1 by L. So b is nothing but minus 1 by L and 1 by L. So strain is given by b. Okay. So the stress is given by exponent into strain. It is nothing but e du. So strain energy stored in the bar is given by half into integral of stress into strain. Okay. Integral upon volume. Then when you try to put all those equations here, substituting stress in EBU, so that will come here. So this is a transpose. When you put these things as a transpose, then you get U transpose, V transpose U. Strain is given by V into U, that is given here. So when you take some of the things out of U transpose, integral of V transpose E, D, D, U, K. So work done by two nodal forces is given by F by Ui, okay, into displacement plus Fj Uj. Uj is a displacement. F. Into this integral factor, U minus U transpose and force. When you apply minimum potential energy by differentiating with respect to displacement, then what will happen? We got F equals to, when you try to differentiate this one with respect to U, we get this function F equals to this integral equation into U. So this is nothing but F equals to force equals to stiffness matrix into U. So this complete factor is known as stiffness matrix. So stiffness matrix we derive using this equation. So integral upon V transpose and small as V integral volume integral. So let us try to, using this equation, let us try to derive stiffness matrix of a spring or bar element. So V transpose is nothing but minus 1 by V, we know 1 by L and minus 1 by L and 1 by L. So when you try to put V transpose, it comes as like this. Then E, then minus 1 by L, 1 by L. So we got EV, right? EV is nothing but A into dx. It's a 1D problem. So we need to take area out. Area is now real constant. Area out, and only x is varying, length is varying here. And so since we have put only length, it is 0 to L integral. So when you write these things common, okay, then we got AE by L into 1 minus 1 minus 1 L. Nothing but K minus K minus K and K. Okay. Using shape functions also we derived how to achieve this stiffness matrix. Now let us discuss on shape functions quadrilateral. So what is linear and what is quadratic? Linear is nothing but the shape functions will be assumed to be linear. So typically it will have only two nodes, whereas quadratic will have mid-side nodes. Okay? There is a node at the center. So what is the difference between linear and quadratic? So accuracy of finite elements can be increased by using displacement where function that fits actual displacement. So this accuracy can be achieved by using quadratic functions. Okay. That is, like if you see actual physics, it should be curvature, but we are assuming linear. We are assuming it's linearly varying. So if you try to put a function which is quadratic, okay, so it will capture the actual physics, actual behavior of the component. So for quadratic it requires additional mid-side nodes. So basic difference is it will have mid-side node and it will have quadratic function. So let us take this same example with mid-side node. Then we need to assume this quadratic shape function, quadratic displacement function. When you try to put these boundary conditions, x equals to xi equals to x equals to xi, we have displacement of at x equals to xj, we have displacement u. At x equals to k, we have uk. When you try to put everything here and try to put it in terms of shape functions, then let us see how it looks like. The shape function looks like this. Okay. So 2 by l square x minus xj into xk, and j is nothing but 2 by l square xi x minus xk, and k is minus 4 by l square x minus xi into x minus xj. So here again same thing. If you try to add nj and k, always the shape functions summation will be unity. And one other important thing is the shape function is unity at ni is having unity value, one value at I, remaining nodes will have 0. Similarly nj will be having 1 here, remaining nodes will be 0. Nk will be having 0 positive 1 at k, and remaining things it is 0. I think now I have to stop here. I have to move on. So any questions I can take it up now. Sorry.